A good hour and a happy life to everyone. Welcome to our channel. In this video, we will explain simple harmonic motion. Some familiar examples of objects that can perform simple harmonic motion are a mass suspended on a spring, pendulum, tuning forks, and vibration of molecules. This type of motion repeats itself over and over again in a constant time interval. We look at the situation of an object with mass m, suspended on a spring with a spring constant k. We see that the object moves down due to the action of gravity, moves up again due to the elastic force provided by the spring. We will notice that there is an interaction between the gravitational force acting on the suspended mass and to the restoring force provided by the spring. By Hooke's law and Newton's law we have k for the spring constant. X stands for the displacement away from the equilibrium position. M stands for the mass. AE stands for the acceleration. The negative sign indicates that the acceleration is opposite the direction of the object's displacement. An acceleration is acting in the opposite direction of the object's velocity. The negative sign also tells us about the nature of the restoring force in the system. We can see that the acceleration is equal to the connection between simple harmonic motion and circular motion is clear when we track the shadow of an object suspended on a spring against a circular background. This movement casts a shadow that seems to traverse the circle as time passes by. The acceleration of the object must be equal to the acceleration of the shadow along the circle. This is given by We also know that there is a relationship between angular velocity and linear velocity, which is given by the acceleration of the object is equal to the acceleration of the shadow along the circle. The left-hand side and right-hand side of the equation is completely equal when we let x is equal to r, and by taking the square root of both sides. The symbol, read as omega, is the symbol for angular velocity. It is related to the square root of the spring constant and the suspended mass. We recall that omega, or angular velocity, is also equal to the change of the measure of the angle in one period t. The amount of time needed to complete one revolution is called period. When the suspended object completes one cycle, so as the shadow of the object along the circle, we say that it had covered 360 degrees in a measure of time. We see that the number of completed cycle per unit time is f, known as the frequency. We notice the relationship between angular velocity, period, and frequency using the equations. We also note that it can be related to the spring constant and the mass of the suspended object by. We see that the period can be expressed using the expression for the frequency is given by. We see that the cyclic recurrence of the motion continues, provided that the magnitude of the restoring force is constant. We realize that if the motion repeats in a regular interval periodically, we can predict the position of the particle at a given time. We can see from the shadow of the object along the circle that its coordinates are given by. We see that the x is also equal to the displacement along the x-axis when the motion is horizontal. We see that the y is also equal to the displacement along the y-axis when the motion is vertical. We compute for the x-coordinate using. We compute for the y-coordinate using where a is equal to r. From the relationships we have seen earlier, we can write the equations for finding the x-coordinate at any given time by. Also, it follows that the y-coordinate can be found at any given time by